Hi everyone, and welcome to Mostly Math. Today, we will be computing some integrals. In particular, we are going to compute the generalization of the Fresnel integrals, which are as follows. I don't know if the S is supposed to be silent. I don't know if it's Fresnel or Fresnel. Hopefully you do. Which are, to go from 0 to infinity with respect to x of cosine of x squared is equal to the integral of 0 to infinity of sine of x squared, which is equal to the square root of pi over 8. These integrals appear everywhere in mathematics and physics. In particular, in physics, they're useful in optics. Note that this is the cosine of x squared, and it is not cosine squared of x. Second one is very easily integrable since it's a simple u substitution. Once you use the form cosine squared x is 1 minus cosine 2x over 2, I believe. Let's see. We plug in x equals 0, we get 1, and it's supposed to be plus. Yep, 1 plus 1 over 2. So if you use that form, you can easily evaluate the cosine squared x. It's a lot harder to evaluate cosine of x squared. You typically do this by contour integrals. This is a very common result. We are not going to repeat it here, but we are going to let 2 be some arbitrary power. So we're talking about integrals like this of x to the a power, where a can be anything. So we can have a is equal to 2 for the case of the Fresnel integrals, or 3, some other integer, have it be 2/3 or 1/2, just to show that you can have a fractional. You can have some irrational results like the square root of 2 and pi. But basically, you just want to plug in any a that it'll converge. I haven't really looked into detail about which a's those are. It doesn't really matter for the purposes of this video since this is a more physics style derivation. So let's begin. In typical physics style, we are going to use complex numbers and consider a somewhat simpler integral. We're going to consider this integral. We're going to have the integral from 0 to infinity. That's too small. Integral from 0 to infinity with respect to x of e to the minus I x to the a. Well, we can obviously see why we're considering a complex integral, because the real and imaginary parts are proportional to these integrals. These ones here. I'll just show you here that this is actually equal to integral from 0 to infinity of cosine x to the a minus I integral of sine x to the a. So we can obviously see why we would want to consider this integral, because the real and imaginary parts of the integrals that we seek. Why we have the minus sign is somewhat mysterious. It'll be made more clear in a moment. In particular, if you don't add the I in beforehand, you have to add it in later so that you can use a special function, which we're going to talk about. So let's just take it as a given for now. Let's begin the rest of the trick, or straightforward derivation. Actually, that was pretty much the only trick. So now we can make an obvious u substitution. We're going to define our new variable t to be I x to the a, which immediately tells us that x is equal to t over I to the 1/8th power. Pretty easy. You just divide by I on both sides and take the 1/8th root, and now we can find what dx is going to be pretty straightforwardly. Tells us that dx is simply 1/a t over I to the 1/a minus 1, and you have to multiply by 1/I here, so just put 1/IA, and we need the dt, of course. This is our new integration variable. As for the limits, they don't change since we're going to consider this only over the reals. So for the purposes of this discussion, we're saying I infinity is equal to infinity, which is not really true, but we are pretty much physicists here, so we're going to say that it's true and that the limits don't change. Perhaps you know a more rigorous way. I mean, I know of one more way. If we wanted to do two U substitutions first, we would, you know, let some variable t be x to the a, and then let some other variable t prime be t over I later. But you still have the problem there when you do the final substitution. So I don't really understand it. I don't really need to, because this is a physics derivation. I'm not a mathematician today, or ever, really. Okay, so now we just plug stuff in. We have 1 over IA coming out front, and we have the limits that don't change. And now we have dt, we have t over I to the 1 over a minus 1 power. And now we have e to the minus t. So it's already looking pretty familiar. We're going to do a further simplification here. And note that 1 over I to the 1 over a minus 1 power is the same thing as I to the 1 minus 1 over a power, which is I times I to the minus 1 over a. And we see that we get some i's canceling here. Yeah, I guess I'll write out another step for you. Yeah, I'll write another step for you. Okay, we get i's canceling, so it becomes 1 over a, which goes back to 0 infinity, dt. We have t to the 1 over a minus 1, e to the minus t, and we also had to put an I to the 1 over a power up front. Minus 1 over a. And now we want to use a special function that you may notice this looks similar to. We're going to use the gamma function, where gamma of some variable x is defined as the integral from 0 to infinity, respect to t of t to the x minus 1, e to the minus t. We're all set up to plug in x equals 1 over a here and write it in terms of our gamma function. I to the minus 1 over a divided by a gamma of 1 over a. It's looking kind of weird at this point. You might ask me where I'm going with this. I'll show you in a moment. Incidentally, I'm going to make use of the property that gamma of x plus 1 is equal to x gamma of x here. It basically just tells you, well, this is the important functional equation used in the definition of the gamma function in some cases. It just shows you that it's a generalization of the factorial function. We're going to combine these 1 over a and gamma of 1 over a terms here. And we're also going to use the fact that I is equal to e to the I pi over 2. You can see this by looking in the complex plane. 90-degree angle corresponds to the point I, so that's all that means really. And this tells us that I to the minus 1 over a power is just e to the I pi over 2 minus 1 over a power, which can finally be expressed as e to the minus I pi over 2a. So it's really, you know, over parentheses 2 over a, but I'm not gonna write that since you can understand. And yep, that's good. So now we have e to the minus I pi over 2a times gamma of 1 over a plus 1 is our final result. I think that's right. Let me just check it. Yep, this is right. And now we are going to do the final simplification here. And note that this is actually equal to just expanding the complex exponential. Cosine of pi over 2a minus I sine pi over 2a times gamma of 1 over a plus 1. So we can see that the real and imaginary parts are the answer that we seek. We can write down here. That's a terrible integral sign. We have the integral from 0 to infinity with respect to x of cosine x to the a equal to the real part of this, so cosine pi over 2a gamma of 1 over a plus 1. Similarly for the sine, we have integral from 0. I can't draw integrals today. Integral from 0 to infinity with respect to x of sine x to the a is equal to, same thing with cosine replaced by sine. All right, this should be right. Doing double check, don't want to give you incorrect information. Yeah, should be okay. We'll see if it's not in a moment. So this is our final answer. As you know, these are not equal in general. They are equal for the Fresnel case. So as a check of this, we would like to see why they become equal, and also just check that it reduces to the value that we think it does for a equals 2. So let's go ahead and do that now. Okay, everyone. Hope you're having a good Sunday. It's really hot here, 90 degrees. Hopefully you're in the pool or something like that. Wish I could be there. Okay. Derivation. Now we have the final answer. We got to plug in some numbers here. All right, Fresnel integrals. Okay, so let's plug in a equals 2. We let a be equal to 2. This tells us that, I'm just going to consider the complex form. So it told us that the integral from 0 to infinity to x of e to the minus I x squared was equal to, I better write down the result just to, I'm using this. Equal to e to the minus I pi over 2a gamma of 1 over a plus 1. It's easier to plug it in one time into the complex form as opposed to 2 times into the real form. Okay, tells us that this integral is equal to e to the minus I pi over 4, because a is equal to 2. We have gamma of 1/2 plus 1, which is equal to 3/2, of course. And there's a couple ways to evaluate gamma of 3/2. Basically, you can just know its value from using it so often, or you can note that gamma of 3/2 is equal to gamma of 1 plus 1, 1/2 plus 1. Just like doing the opposite of what we did, basically. Which is equal to 1/2 gamma of 1/2, following from this identity. Hopefully this is just a brief review of how to do this. And we know that gamma of 1/2 is square root of pi, so the value is square root of pi over 2. I just knew this because we use gamma of 3/2 pretty frequently. But if you don't, it's fine. You can always do this, and you have to remember that gamma of 1/2 is square root of pi. You just have to do that. I mean, I can't help you if you don't know that. All right, so that's the easy evaluation of gamma of 3/2. And it's pretty easy to evaluate the exponential as well. So we got square root of pi over 2. We have cosine pi over 4 minus I sine pi over 4. Hopefully everybody knows what these trigonometric values are. And obviously they're both equal to 1 over square root of 2. So we can see why the integrals are equal, because the cosine and sine function are equal at this point. And now we can simplify. We got a square root of 2 and a 2 here. We want to bring the 2 inside, so 2 square roots of 2 is equal to 4. Square root of 4 times 2, which is a square root of 8, of course. So we can bring the 2 into the square root if we write it as 8. So we get square root of pi over 8, 1 minus I, and this actually tells us what we need. It tells us that the real and imaginary parts are equal. It tells us what we want, basically. So integral from 0 to infinity dx cosine x squared is equal to the real part, square root of pi over 8. And integral from 0 to infinity of sine of x squared is equal to minus the imaginary part, because the original integral has a minus sign in it, is equal to the square root of pi over 8 as well. Wrong way. The 8 goes inside. Very famous number, square root of pi over 8 as well. So it definitely simplifies in the case of the Fresnel integrals to the values that we know. And just for some final thoughts here, can we go further? Can we plug in 8 equals 3, for example, and get something in terms like, integral from 0 to infinity of sine x cubed is going to be some function of the square root of pi, and then you got some other function of like the square root of 2, something like that. Like what we had here with the evaluation of the gamma function. Unfortunately, no. It's not really a function of that. You can simplify cosine pi over 8 and so forth to get nested radicals. But the gamma of 1/3 does not simplify. So this integral is going to be in terms of cosine pi over 8 and gamma of 1/3. You can simplify cosine pi over 8 and you can't simplify gamma of 1/3. So it's not as useful to calculate because you still have a special function there. And the trend will continue on as a increases. By the time you get to a equals 6, you can't simplify any of them, or at least you can't simplify them easily. And it's not very useful to plug in specific values. It's more useful as just a general formula. If you had an integral of this form, or perhaps for numerical purposes, this would also work. But you can't really go much further than that. It's mostly just a cool derivation showing off my mastery of the gamma function, basically. It's not really that impressive. You just have to notice that if you have a polynomial times an decaying exponential, you can write it in terms of the gamma function. You can do the same thing. And if you enjoyed this, want to see more, please feel free to subscribe to my channel. I'll see you next time.